Well, I think we can go ahead and get started. So welcome to the first CITA seminar of the semester. And today we're very lucky to hear from our very own Guo Xu, who's a CITA fellow and a Schmidt AI for Science fellow, those words in some order. And before coming to Toronto last year, Guo was Origins postdoctoral fellow at the University of Virginia. And before that, he got his PhD at the University of Texas at Austin. So today he'll be telling us about AI for Astro.
Thank you for my introduction. So today I will introduce my dissertation work, plus my postdoc work, and also the work at CITA. So it's one kind of a gallery of all my work using AI to study star formation and this medium. So let's get started with some nice movie. So this is the MHD simulation from StarForge, modeling a cloud formation and also star formation. So we can see under the gravity, turbulence, and magnetic fields, all these physical processes interplay with each other. They will form stars. And during the star formation process, they will launch outflows, jets, stellar wind-driven bubbles, radiation-driven bubbles, and all this feedback mechanism will inject energy, momentum to the surrounding gas. And also, feedback will reduce the accretion rate of the star. So that means the final, well, it's going to start here. So the final initial mass function from star will be regulated by all these processes. So star formation is very important because it regulates for the evolution of a galaxy and also the evolution of its cloud. But studying them in detail is really tricky because we have tons of non-physical processes, as we mentioned before. And in turn, once a star formed, they will have feedback. So this interloop or coupled processes will mix together. Because it's difficult to disentangle each individual physical processes to study them in detail of how star form or what the physical processes regulate star formation. And then, from observational perspective, it's also difficult because, such as from radio swarm observation or in sub-millimeter or millimeter observation, we have position, velocity, three-dimensional data cube. So for human, we are not that okay or satisfied with the 3D volume data. So that's challenging for us to scan this data slice by slice or channel by channel. And then there is a huge question or challenging part, not only in star formation, but also in astronomy. That's how can we compare from simulation to observation? Since that's always the tricky part, because in simulation or in theory, we know what the physical process is, we know what the condition is, but we only know what's the most dominant part. In reality, in observation, there are tons of the microphysics happening, and they interplay with each other. And we only have the first order approximation from simulation or from theory. So we want to retrieve from observables, such as from EM or from any luminosity or from spectrum, to infer what the intrinsic physical processes or intrinsic physical conditions. That's really tricky because they have a lot of degeneracy. So that makes these things really complicated and really tricky. So in this talk, I will try to answer two main questions. So first is from star formation perspective. What is the impact of stellar feedback to star formation and also in multi-cloud or their birthplace? And then I want to know, can we infer the physical processes from observables in their molecular cloud or in ISM? To answer these two questions, we have to go from both ways. One is from observation. So that means to study stellar feedback, we need more samples, or we need more observables or some constraints from observation to let us know a complete sample to do statistical study to know how feedback look like and what is the energy, what is the mass that feedback is from observable constraints. And from the other approach, we have to go back to simulation or theory because we know what if the condition is, what if their physical law is, to study what the physics behind this star formation or ISM. So to solve these two question. We cannot do it by our human because especially inferring to the quantities from observables is actually tricky, and there are a lot of geometries. So that's why we're starting from AI to help us, and also from observables as well, because there are tons of data and it's really complex. So I will show some examples how AI can help us to solve this problem from both observables and also theory or simulation. So let's talk about feedback first. So as you can see from the movie, feedback has dramatic impact on the morphology or reshape the cloud or ISM. And also they have great impact on the most fundamental quantity, IMF, initial mass function. We know in simulation, we can control whether we can turn on or turn off feedback. So for example, if we do not have any feedback in a simulation, we just have a gas, accreting gas, the particle accreting gas, and then we will form more massive stars. But if we turn on feedback, then we'll significantly reduce the star accretion and also the final mass from accretion. So that means we will have more mass stars. And compared to the slope, what we observed from decades ago, such as from CITA, that's the IMF slope. If we have feedback, the slope is almost identical to this IMF slope. And also we can reproduce the turnover point that's around 0.5 solar mass because we have less from north if they have turnover. They are not going all the way up. And to study feedback, we need to constrain that from observation first, because we don't know what is energy, what is momentum look like. And also, it's a really tedious work. We want to identify them. So for example, celebrating during the bubbles, it's a more shell-like or circle-like structure. There are proto stars, and we will blow up this bubble. This is a position velocity integrated emission from CO or other molecular cloud or other molecular line emission. And we can see there are also some turbulent patterns can represent similar structures. These are fake structures and not bubbles. So human will have some bias towards identifying bubbles. So that's challenging. We might have some false detection. It's not easy to do that pixel by pixel labeling of where the feedback is. So we started on a really simple try. So we're starting with some really simple network, not network, a simple machine learning algorithm. This is a random forest spatial decision tree. Just to tell us if there a feedback or not in the postage stamp of the observation, such as if there feedback or not, we will just return you yes or no. So this is a decision tree based on certain criteria. We can distinguish whether this image contains feedback or not. And we train our algorithm with nuclear project. So that's the Spitzer survey combined with the citizen science labeled bubble location and postage stamp. And we also implement some of the additional data set that's coming from simulation, because humans have bias. From what I've seen from nuclear project, humans always identify the bright, luminous, bright, or really luminant bubbles. They are missing some of the faint or ambiguous bubbles. So simulation, we can generate more bubbles that are driven by lower massive stars, such as B-type or even A-type stars. And then we're adding that as a conditional training set to train our algorithm. And this is the new bubble being identified in the nuclear project from Spitzer survey. By we train algorithm on additional data set. So that means simulation can help a lot to reduce the bias of the training set. So this can give us some confidence that simulation can help a lot for machine learning training. So that's the next step we want to do, starting with purely simulation to identify feedback on pixel level, rather than just post stamp tell us yes or no. I want to do a pixel by pixel masking of the location of feedback. So in simulation, we can trace where the feedback is because we have the tracer particles to trace the location of feedback from the young stars. And then we have this accurate mask. We conduct synthetic observation to generate what we observe, such as the CO line or other molecular line tracers. And then we train a neural network. This is an autoencoder neural network. The input will be position velocity, three-dimensional data cube, what we observe from actual observed data. And output will be the mask, the location of where the feedback is. So this will give you really high level, high precision identification of feedback gas. So here are some illustrations of what the traditional method give you. We just simply put a mask on a three-dimensional PPV cube across all velocities. So this contains a lot of contamination from ambient gas. Here, machine learning will give you more pixel by pixel level of the location of where the feedback is. So this is really promising for us to have better quantification of both mass of the quantities of feedback. So with that pixel level masking, then we can do better quantification of their mass energy momentum. So if we apply to a traditional masking, circular masking, we will get almost 3 times more overestimating on their mass, and also for energy, for momentum. And for AI testing, we test on synthetic data where we know what is true outflow or bubble mass is, and then we get almost on the one-to-one line. So this is really promising. We can better quantify the energy budget of the cloud. On the other hand, machine can give you more comprehensive scanning or survey on the micro cloud. This is torus. The red circle, or not circle, the red square targeting the previously identified bubbles, and all the yellow ones are the newly identified bubbles. And young stars also labeled in red stars. So we are identifying more bubbles, but we are quantifying to a lower mass. So there are some trade-off, and fortunately, the result is consistent with what previous people did. So I would say previous people get a right result going to a wrong way because they are overestimating the mass, but have less sample. They are missing out the sample. But we are correcting the mass, they have more complete sample. We get almost identical result. So the takeaway is feedback energy is sufficient to compensate the turbulent dissipation of the cloud. So cloud will not undergo broken collapse on a 3-4 time scale. Feedback will always replenish this dissipation to maintain and support the cloud from being continual collapse. So this is the main takeaway from the energy budget analysis. And with this high fidelity outflow or bubble sample, we can do more analysis, such as this is the outflow we identified in our wine molecular cloud. And we can study a lot of the physical statistics, such as the power spectrum. We study the spatial power spectrum of the main cloud and also the feedback region. And we see in the feedback region, there is a break power law. This break scale is on the order of half parsecond. That's consistent with the typical outflow scale. So that might indicate some either mass injection scale or energy injection scale to the molecular cloud to maintain turbulence. So that may be a typical injection scale for turbulence. And then we also do statistics study on outflow launching axis. So simple way, there are a lot of outflows. They are launching usually randomly from our intuition, but we see there are some correlation with their orientation. The closer to the outflow to each other, the more alignment of the outflow is. If they go further away, they're almost to a random distribution. This is a 3-dimensional projection because machine learning can give you the prediction of the inclination angle of the outflow as well, and also we have the position angle. So we have some self-correlated regulation of outflows. And then we also study how magnetic fields regulate the launching axis of outflow. We compare not on the small scale. This is E field is for large scale. This E field is from Planck, so this is really large scale magnetic fields. Usually we do not expect any impact from the large scale E field to impact the outflow launch axis. The outflow is really local, it's a core scale, really sensitive to their own acceleration or angular momentum. But we see there are some trend of alignment with the outflow launching axis versus the large scale B field. So outflow might have some imprint or have some information from the large scale cloud during the collapse or formation of the core, dense core axis, and also the accretion axis. And besides the entire survey of outflows, we can also to study outflows individually. So we also train a neural network that's a multimodality learning. So not only considering the images, but also considering the spectrum. So this is taking both the integrated two-lobe or two-channel blue-shifted, red-shifted lobe outflow images, plus the spectrum from ALMA to infer the outflow mass and also the inclination angle and also position angle of outflows. And for this neural network, we are also doing the prediction with uncertainty. So we can more quantify how reliable of this prediction of this algorithm is. And to be more straightforward, I can show you the performance. And for example, we have several snapshots of the outflow, and then for the prediction, testing, since testing set is not including our training, and they're all doing really good job on both sparse mass, inclination angle, and also position angle. And we also try using some occlusion test or analysis to know whether machines are doing reasonable job because we want to do a more explainable machine learning algorithm. And we can random mask part of the patch in the images, and then to pass into the algorithm to see whether they will impact algorithm prediction a lot. So that indicates where the red is that impact the final output more. So this is an importance map. So that's really making sense because all the prediction is sensitive to the outflow lobes, and also this is the mass prediction that really matters with their opening angle. So because we have higher mass of stars, usually they have higher opening angle of the outflows. And this gives us some confidence machines doing some reasonable job. They are not looking at random part of the image. They are looking at what is most important physically. So apart from feedback, let's go to a more interesting part. That's inferring physical properties from machine learning. So in astronomy, this is always really challenging. Going forward, that's straightforward because we are doing simulation and also doing the transfer to using what we know from the equation or know from the physics, starting with either density, velocity, and then guided by Navier-Stokes equation. We can get what the final evolution stage is, and then we can conduct synthetic equation to generate dust emission or line emission. And this is what we actually observe. But if we have some observables, such as from the telescope, we want to infer back to what the physical quantity is. That's always challenging because degeneracy, as we mentioned before. And then if we want to do a one-to-one mapping, we have to explore a wide range of parameter space. That's really computationally expensive. So that's why I hope to use AI to help us do this reverse process to better or accurately to infer what the physical condition is based on certain observables. So what we are using for the algorithm is a diffusion model that's widely used in industry. So diffusion model, conditional diffusion model. So for example, they require some condition or prompts, such as we have the input of cat, and then diffusion model will generate this image for you. And what we want to do is, given some observables, such as column density, plus some coloration measurement from dust, we want them to recover what the volume density is, what the B field look like. So that is what the basic idea of this diffusion model. Given certain observables to infer the intrinsic quantities. The basic mathematics is really straightforward for diffusion model because this diffusion process from observables, not observable, this is the intrinsic quantities to purely random Gaussian. this is purely random walk by gradually adding Gaussian noise. And this can be modeled by this random walk. But what diffusion model do is to model the reverse part. They want to learn how can we, starting with random noise, given some observables or prior, to propagate back, gradually denoising to what the phase quantity is. So the machine is learned this reverse process. And the general training for the machine learning, especially for diffusion model, is really straightforward. And the math is simple. But the downside is it's pretty slow. Usually it takes weeks for decent convergence. And I will give you some example for how diffusion model works in some of the inference of quantities. So first, let's look at the volume density or number density. This is a key quantity in star formation or in ISM or in astronomy because column density is just accumulated density around site. But what actually regulates the evolution of the system is their intrinsic volume density or number density. And there are free-fall time scale and also star formation rate, star formation efficiency, and also chemical reaction also measures the number density. The way we measure the number density from ISM is really using a density tracer such as HC3M. To observe this multiple line transition, this is really expensive. Usually takes at least tens of hours to get sufficient signal-to-noise ratio. So that's too expensive. So that's our intuition would be, can we, starting from the easy to get observation, such as dust continuum, that can be taken just in seconds, compared to this tens of hours, to infer what the volume density look like from what we easy to get column density map. So we train this diffusion model with the magnetic simulation covering a wide range of primary space, including different dynamics, different B field, and different energy stage. And this is an illustration of how diffusion model work from a purely random Gaussian noise distribution to the physical properties. This is the number density. This is the column density, is the input in observables. And here are some model performance. So people usually do some of the power law conversion, such as there is always following some index from column density to volume density. And we adopt several power law fittings, and we can see their scatter is large and is unsymmetric across different density scales. And also we train a simple neural network. The performance is also acceptable, but still not good. Diffusion model is the best, and it's more symmetry in their error. So this gives us some confidence. They are doing a really perfect job to infer the intrinsic field quantities using diffusion model. And we also test on real data. So this is the torus molecular cloud filaments. It's the B213 filaments. And there is one observation, only one observation, targeted towards the dense part of this filament. And they are taking tens of hours from the telescope using GPT and also several other telescopes to observe the density tracers. And they constrain the volume density in that part. And our model just taking from, this is simply from Planck plus Herschel map, derived column density map to infer this volume density. It's identical. The error is less than several percent. So that's really promising for us. So we can achieve some of the quantities that requires expensive data set. So with machine learning, we can do more science without using tons of telescope time. We can use some of the low quality data to do more advanced science. So with better data, machine learning can do even better. So that's a promising part for machine. And so people may ask, you are training on some of data and testing observation. Will that have some bias? Or will that perform good on other type of data? So we did some tests. So in simulation, when we do the training, we only train on one type of simulation, that's the cloud collision or non-collision with gravity and they are forming stars. But here, we are running a new simulation with different code. This is the Pluto-based code, AMR also. And then we are running purely turbulence. So no gravity, there is only magnetic fields plus turbulence. And you can see this is the column density versus density distribution. Our new data set is not similar to what the trained data look like. However, when we apply our trained diffusion model to this new data set, compared to other traditional methods, this is the power conversion that's always offset. And even for machine learning, this is convolutional network. It's a simple machine learning method. We also have some offset. Diffusion model almost centered at 0. This is error, and then small symmetry. So diffusion model can learn some of the out of domain knowledge. So that means in astronomy, we always know part of the physical processes. We are not able to model or simulate exactly the same of the observational condition. So this ability is important when we use to extrapolate our knowledge to the unknowns. So for example, we only can model what gravity, what turbulence, what magnetic fields regulate, but there are some of the macrophysics unknown. They will also impact. This can learn part of that to smartly to broaden this knowledge horizon. So this is promising. Although we are still not fully understanding what happened, but from a performance perspective, it's pretty promising. And they can provide some insight for us, especially when we want to explore some of the new knowledge or new domain. And another test is straightforward, radiation field. Radiation field is everywhere in astronomy, especially in interstellar radiation field, it's everywhere. And it's energy source, and also it will matters with the feedback and radiation pressure. And observe that it's also really tricky. Either we rely on some of the atomic line, or we have to integrate over our dust emission to do some assumption to convert back to radiation field. And in simulation, we can exactly trace each band of the radiation field. So that's why we are using simulation to train our algorithm and to test on real-world observation. To generate training set, this is really tricky because we do not know what a star property look like. So we have to explore different simulation and to assume different SCDs for the stars and to conduct a lot of the power space to enhance the diversity of training set to generate a certain other black body SCD for stars or some of the young YSO SCDs to generate synthetic data to train our algorithm. This radiation field is from the simulation. We know the ground truth. And luckily, our synthetic data can cover what we observe. So all the blue dotted data points are the real observed SCDs from Spitzer and also Herschel. These are Spitzer bands, 3.5, 4.5, and 5.8, and these are 250, 350, 500 from Herschel. And on the background are the SCDs and also synthetic data. So here are the performance. Ground truth. This is a prediction. Almost perfectly recovered what radiation look like in a piece of cloud. And to be more quantitatively, so this is the radiation field ground truth. This is the prediction on the one-to-one line perfectly. And also, we run synthetic data with new dust models so that to test whether the model is robust when they encounter different physical properties. Also, back, there are some scatter. This is a pair of 10 difference. Yeah. And we also do extreme test. In simulation, we can turn on or modify the radiation field, ambient radiation field, arbitrarily. So this is actually increase radiation field by a factor of 100, and the model still give you reasonable trend, although there are some offset because model never seen that radiation field before, so they always underestimate this radiation field, this system. But still give you some insight on how the radiation field distribution look like in the image. So based on what I've shown before, so DDPM have shown good potential to explore some of our unknown data or unknown image or unknown knowledge in astronomy. This is a really straightforward test on real data. This is a mono-R2 observation, mono-R2 observed by Spitzer and also Herschel, and this is a multi-band dust emission. And this is what the radiation field looks like. It's consistent because this place is where the star mostly formed as the most active region, and the radiation field is intense and similarly here. So we are doing a reasonable job, at least. To evaluate that, then we need to do more observation to constrain whether our result is robust or not. But we do not have that large map radiation field map. So that's the issue. And some of you they ask, radiation field usually correlated with dust. Whether dust temperature can be a representative to radiation field. From our test, seems no. This is in fact observation, since we know what the dust temperature is because we know the star property and we do the transfer, and we know the dust composition and we know each composition of the dust temperature. And then we plot the temperature of dust and the radiation field. It's not on the one-to-one line, so it's really blobby or chunk distributed. And this is the mono-R2 region. Both, they are not similar. And this dotted line is the previous, kind of the traditional conversion, assuming some gray body to, since beta is the emissivity here. No. So the possibility for this offset might caused by extinction from our understanding is because radiation field is really local, but what we observe is always being extinguished by line of sight gas and dust. So that might cause why the multiple component dust fitting is not working in that case. And then the most interesting part, magnetic fields. This is always a challenging part for astronomy. Difficult to measure and difficult to observe, but it's important. It's everywhere. B field is everywhere, and it regulates over the universe, regulate the structure formation, regulate the cloud formation, regulate also cosmic ray propagation or acceleration. And so, for example, here, the B field is consistent with the structure of this fiber structure. And also, this is the molecular line, a molecular observation. Also, this B field has a consistent orientation versus the structure orientation. So, important, however, not that easy to observe. So in observation perspective, we have two components to observe. One is line of sight, usually use Zeeman. The other is the black sky, usually from polar radiation, either from dust or synchrotron or starlight. So these two combined together can give you a more comprehensive understanding of how B field look like. But from my understanding, it's not easy to combine these two because Zeeman, either from H1 or from OH or from CCS, even denser tracer, or CN, they are missing the part of dust emission. So there is no kind of in the intermediate translucent cloud scale Zeeman observation. So if you want to know what is the B field in molecular cloud, it's always changing. Since Zeeman only gives you H1, that is more surface of the cloud, rather than the actual molecular cloud. For dust, they only give you line of sky, not the line of sight. And people always trust Zeeman, but from our test, Zeeman is not that trustworthy. So we conduct synthetic observation on a piece of cloud. This is the H1 column density, and this is the H2 column density, because in StarForge simulation, we can trace the chemical evolution of the gas, or we can trace the composition of the gas more accurately. So we know the H1 density, temperature, and velocity, all kind of synthetic vision. Then we can generate synthetic Stokes I. This is the total intensity, and also Stokes V. That's the polarization spectrum. And we will conduct multi-Gaussian modeling to split all these Gaussian components. But the reality is the actual B field on the outside for the spectrum is highly complex. So for example, for this spectrum, the actual BC line of sight magnetic field is flipping. So this is positive, and then this is a dotted line. This the BC is flipped. So we are factoring a lot. It's not a constant number, and also what we observe is in velocity space. It's not in physical space. This is in physical space. So it's not difficult to disentangle each other. And we calculate for each component what is the contribution of the gas of the magnetic field in this portion. So that's the ground truth compared with what the fitted value is. So we can compare the ground truth versus prediction. And from our fitting distribution seems okay, and this is the true B field calculated by knowing which portion of the gas contributing to that velocity range. And seems promising, they are always predicting similar distribution. But when we do the comparison of these two, the true minus fitted, there is always a factor of 100% sense of factor of 1 or 2 uncertainty. And the absolute error for the difference is on the order of 10 microgauss. This is significant because H1 you trace a gas on the order of 10 microgauss. So that means if you see some observation of Zeeman for H1, they mention as 10 microgauss, they be cautious. That might be 0 or 20. So that can be a factor of 2 difference for that. So Zeeman is not fully trustworthy. How about DCF, the plane of sky component? Also not that good, because the plane of sky measurement always rely on assumption. This is the Fermi assumption, because the big assumption is turbulent energy is equal to the magnetic energy. So if there's a strong field, the field is more guided, it's more orientated to one direction. If the field is weak, it's more disordered and then more mixed. So you can compare with the dispersion of the angle from observation to infer what the actual plane of sky B field is. There are different versions of the DCF method, but the base idea is the same, always inverse proportional to the dispersion of angle. And to solve that, we try to use diffusion model to help us to quantify B field. So we train the model similarly on a variety of simulation. So different unit stage, different B field, and then we generate training set. So we have column density, we have coloration map, and we have line of sight velocity dispersion. That gives you some information on turbulent energy. And then the air output will be the pixel level B field prediction. And for the performance, seems promising. So this is a column density map, and this is a ground truth what the B field should look like, ranging from 10 microgauss all the way to several hundred microgauss. And we train the diffusion model by taking different type of input. And the takeaway is, same diffusion model give you pretty good prediction compared to what Quadrant's law might give you. Quadrant's law is density versus B field. They have some power law conversion. And we are doing not bad at this, and we are doing more pixel by pixel prediction. And we also do some tests on new simulation. So in that simulation, we'll have no gravity or with gravity, with outflows, and have different mass to flux ratios that indicate different B field and also different arc product, different density. And for some of the parameters, they are doing really good, consistent, but for some, they're offset by a lot. But diffusion model, look at the 3 channel, the pink one, is always near the center. So compared to what power law training data gave you. So diffusion model always can correct for this offset on new data set compared to what you have derived from original data set. Such as you observe one system, you derive some empirical law to do conversion between two physical quantities, and you want to apply that to a new physical system, then usually that failed. A diffusion model can help you to reduce that bias. So that's the promising part using diffusion model to do transfer learning or transfer knowledge from one system to the other. And more straightforward comparison with DCF. DCF is disaster, especially when you look at the relative adder that is only order of 10 or 18, and diffusion model usually give you pretty small. And from the map, the DCF is always overestimated by a lot. So we always be cautious on what DCF and Z-map give you, and always check multiple sources of observations to constrain the B field. And I want to also introduce some of the new work we have been doing. Instead of diffusion model is based on the diffusion process, and then we are modeling from random noise to our target. And we're developing a new framework that's a Schrodinger bridge. So that's instead of starting from the purely Gaussian distribution, we're directly starting from observables. So Schrodinger bridge will bridge the path between observables to our physical quantities directly by building a pathway directly. And Schrodinger bridge is based on a stochastic differential equation. So they have a better, or compared to DTM, they're same. They're all based on stochastic process. So they have the same ability to extend to unknown data set. So I can show you one example how our Schrodinger bridge perform on a new data set that has never been seen before. This is what we trained and tested on the same type of data. Although the testing data is not included, but the source of data is coming from the same, because they are all following the same equation and from the same code. So they have some intrinsic bias when they're doing the training. And then Schrodinger bridge performance is similar to the diffusion model. But when we test on new simulation that's run by different code with different physical assumption, different physical condition or boundary condition, we can see there is a huge difference. Diffusion model also picks around center, but we have some long tail. But Schrodinger bridge result always give you the best or really center picked. So that's the promising part for astronomy, as we mentioned. So if we have some empirical law derived from one system, are we safe to explore or extend to a new system? Schrodinger bridge might be a good way to try. So they can help you to reduce the bias between different data sets and then to do more robust prediction. And I think I can stop here and take any questions. The main takeaway is AI can help you a lot in studying star formation and intermediate, and also definitely in astronomy. So just try that, and AI is evolving really fast. So thank you.
Yeah, nice talk. You covered a lot of ground. My question is about the feedback in your models. So there's some description for how the feedback happens, right?
Yes.
So maybe describe briefly what that description is. But my real question is, how does the result vary if you change that description?
That's a good point. Yeah, that's a really good question. So the feedback prescription is all from the Cunningham papers. That's a 2011 paper. So that means when we're doing the accretion, and then 30% of the gas will be returning back to the surrounding. And the launching axis is the angular momentum of the core. So that's a basic assumption. And the launching velocity is the Cavalier velocity of the disk. So that's the basic prescription. And if we change the prescription, whether we will change that will definitely change our training. That's definitely true. But that will not significantly change how we mask the data set. Because from what we have during the training, we have seen is, even though we lower down the feedback, since we have different mass of the core, so they have different strengths or intensity of the feedback, the morphology really consistent. And also from the position velocity map, we always see those voxels are infected by feedback. So even we turn down feedback fraction, in terms of masking, there will be minimum impact. But for quantification of mass, there will be yes, because machine will always predict the fraction of feedback in that voxel. If the penetration change, that will give you some different answer. So that's why we want to apply to real data to check if the real data give you some dramatic different morphology of the outflow cavity or outflow shape, that might indicate there might be something need to modify in our prescription because we are not covering that kind of the physical phenomenon or physical process. So that's a look back when we apply to real data, and real data will give us some hints or insights on whether our prescription is yes or not, whether it's correct or not. So that's true, but currently, from a masking perspective, it's okay. But for quantification, there still need to be improved and to be more testing and evaluate from the real data.
Are there any questions online? Oh, yeah,
Very nice, Johan. Sorry, can I just ask you? So here you train your model on the star forge, but ideally, how many different kinds of simulations would you like to train this on? And I'm also really curious to know for star forge, how many snapshots do you need, or what cadence do you actually need to be able to train these models properly?
Yeah, for example, in our radiation field, we are training a lot on star forge, and we are choosing different alpha parameter, different B field, and we also train for different initialized radiation field, different turbulence initialization. And for the training set perspective, for simulation, there might be on the order of several tens or 50 or 60 different HDM5 files. But for post-process, we need to do a transfer to generate dust emission. We have to do zoom in. So that'll give you one HDM5 file will give you almost hundreds or even thousands patches of the dust emission. So in total, we have almost several tens of thousands snapshots for training for dust. And for B field, it's on a similar order, although it's not on star forge, but similar order. And for DDPM, that's a little downside of DDPM. If you want to do a really convergence training, you definitely require more data set. Since it's a stochastic kind of the equation. And if I training a flow-based model, that's another machine learning type of model. They are based on the ordinary differential equation. That requires less data. But the heavy-based flow-based model will give you less diversity. And that might give you some really biased result towards your simulation rather than real observation, because they always learn a deterministic process. Yeah. But better, the more data, the better, usually, because the machine will learn more comprehensive global view on the data distribution.
I think she was asking more about, like, if you were using star forge, suppose you take Orion simulations from the bird.
Yeah.
Have you looked at those at all? Did they give you any different results?
Yeah, we are doing that actually. So all my tests is on Orion simulation, and the training usually is from. So for example, for this test is from Orion simulation. We have the turn-on gravity or turn-off, and for Star Forge and Orion conversion, I haven't done that because for the training it is from ISM simulation. That's another type of simulation. For the feedback prescription, I would say they are identical. Because what I know, that's identical because my goodish are using the identical from status group, But for other treatments such as heating, cooling, and radiation, they have more physics in Starforge but not in Orion. So that will give you some significant change on the final density distribution, temperature distribution, and the column morphology. That will give you some significant difference.
So have you quantified how different they are, the different simulations?
Not yet, but before, what I know is Standard did some quantification of core mass function IMF between the two framework of Orion and Starforge. Orion has an issue because Orion, due to their maybe not that optimized, so they are not able to form really massive star and then evolve quickly. So getting stuck on a certain point, and from that distribution seems not that the same. There's still some discrepancy. Starforge will better optimized routine and then will do much faster, and then you can all the way model into the supernova. And core mass function, my impression would be somewhat similar. Core mass function, but in IMF is not. My impression would be. That means the earlier stage. Yeah. Similar.
There are other groups too. There's the group in Germany with
Flash.
using Flash, and then there's people in Australia as well doing simulations. It'd be interesting to, take the snapshots from those different codes and see how well people are actually doing.
Yeah.
Really interesting. Quick question. So for different initial realizations of the Gaussian units in your diffusive models, do you ever find that you converge to multimodal output spaces, or do you end up getting the same return time?
That's the point. So we have tried different initialization for the inference stage, and it's always the same answer. The uncertainty is on the order of 10%, less than 10%, so it's 0.1. So that's really small compared to what astronomy usually has, the error bars. And the takeaway we have is they are strongly conditional deterministic. The condition will always guide you what way to go from either random noise. And also we tried, there's an eta parameter, that's how stochastic of the model is, and also converge to similar results. So it's all physics, kind of a physics guided inference.
I had a question actually about these relative error problems you've been showing, and you've been highlighting that it's important for it to be centered at zero so you don't get an overall bias. But I was wondering about the shape of the distributions and also, like, is there any calibration you need to do to the width of the errors, and are these errors used in any downstream analyses, and is there?
This value error here analysis is really brute force. So we are doing prediction minus true divided by the minimum of prediction or true, the absolute value of prediction or true. So it's really brute force to see how offset compared to the true quantity. So we are not dividing by the true, because if you are doing the true, some of the time true is 10 microgauss, the prediction is 0, so then that will give you 0 better error. But we don't want to do that because the actual difference is large for this two quantity.
Okay, yeah, I guess do you assign errors to the prediction, and do they?
Yeah. For this work, we did assign for the uncertainty here. But for the other work, well, ongoing, yes, we'll assign the prediction error, predicted error, so that will give you the predicted plus or minus of each quantity, and then we can quantify for how reliable that is. And for that prediction, what we are saying is this is really small compared to what we got for the actual true minus predict is. So this error is on the order of 1 or 2%, but actual true minus predict is large. So that means modeling for the magnifield's prediction. So that's unfair comparison. So for this model, they are giving you the prediction of the error plus or minus 1% or really small number. But for B field, the actual relative error of true and predict, that's on the order of 100%. So that's offset by a factor of 1. So that's non-fair. But yes, if you want to incorporate, I have to think about how to do that smartly, because this will give you 1 sigma, and then we'll do the computation of predict and true that will propagate to that quantification. Well, broaden a little bit on this true minus predict. Yeah. Yeah, for that plot, we didn't incorporate the uncertainty. Yeah, since we don't have that in our measurable prediction. But for this model, yes. I haven't plotted that yet. Yeah.
Are there any other questions?
There are questions online.
Oh.
Oh, yeah, further rotation is another thing. Yeah, further rotation, but that requires the assumption of the electron density as well. So that's adding 1 more uncertainty. Since further rotation is the NE times B integral. So that might give you another uncertainty, but definitely that'll give you some hint for B field observation. So that's the also give you some line sight information. Not left, yeah, left. Information. Yes. Yes, that's the possible way you can try in the future, combining all different type of observation. That's AI can do, because AI can adapt different type of data modality, and they can integrate them smartly to do a comprehensive understanding of the data and do inference.
Yeah, sorry, this is a very, very specific question. In the plots that you had where you showed that the marginals of the prediction versus the truth were the same, but then the differences had a width of the same size as the marginals. Do you remember which one I'm talking about?
You mean the B field one, or?
So I can't remember which variable you were plotting, but you had, it was some non-trivial structure in like the predicted distribution with multimodal, but then when you did the differences between them, it was 100%. Yeah, this is it. Or this is
I don't think it was this.
For this one, I guess. The prediction versus true, so there are several predictions. For this one. For this one.
well, given the time, I suggest that I'll follow up and see what for it.
Or discuss it offline.
Yeah.
Okay, cool. Yeah, so we are at the hour. Discussion can continue upstairs in the CITA deli. When there's some like